Hello everyone, thank you for joining this presentation. My name is Tim Slangen, PhD candidate at Eindhoven University of Technology, the Netherlands, and I will be presenting this paper to you about the effects of high-frequency residual currents on the operation of residual current devices. So this is the poster corresponding to the paper, and I will discuss each part with you in the next few slides. Starting with the abstract. This research investigates the effects of high-frequency currents between 50 Hz and 150 kHz. Part of this range, 2 to 150 kHz, is the supraharmonic range on the operation of residual current devices, also called RCDs. And the purpose of an RCD is to detect earth fault currents and to prevent humans and animals from dangerous currents to the body and to protect installations against fires. A setup is developed to introduce both 50 Hz and high-frequency leakage currents at the same time and also individually, and the tripping current for non-nominal frequencies between 50 and 150 kHz is determined to verify the possibility for false tripping, and also the 50 Hz tripping current for the RCDs is tested in the presence of a high-frequency current. So false tripping means that the RCD trips in the case when it shouldn't, so when there's no earth fault current present, the RCD shouldn't trip. And the other case is a false negative. That's a case in which the RCD does not trip, whereas there is a dangerous leakage current present. And the most important conclusion is that the RCDs of type A and AC have an increased fundamental 50 Hz tripping current when there are when there are high frequency components present. And this potentially results in a safety risk. A test setup was developed to test the different RCDs in different scenarios. The goal was to be able to introduce both high-frequency residual currents and 50 Hz residual currents individually and at the same time to test the behavior of those on the working of the RCDs. Only 4-pole RCDs were used because they have a combined measurement of all phases, which means that there's one primary coil measuring all 3 phases and the neutral, and it will trip if there is a delta difference between the current returning and the current flowing into the system. And in this way, we were able to inject high-frequency residual currents non-returning via the RCD and 50 Hz residual currents also non-returning at the different poles of the RCD. And the poles phase 1 and neutral were used to feed a small resistive load, and the mains was supplying power to the RCD because some RCDs need 230 volts from the mains to operate. 2 function generators connected to small resistive loads and 2 amplifiers were used to inject the high frequency and also the 50 Hz leakage currents. The 5 different RCDs of types A, AC, and type B are tested. Type A is mostly used in residential installations for the detection of sinusoidal or pulse DC faults. And also type B is used in installations where smooth DC faults above 6 milliamps can occur, and where no other protection against these DC leakage currents is installed. So for instance, installations with EV charging or PV installations have a recommendation to use a type B. Type AC is currently not used that much anymore because it is unable to detect pulsed faults, which can be dangerous. So in the figure below, you see the I fund represents the created fundamental current, the function generator, and the amplifier, and the same for IHF is a high frequency current between 50 and 150 kHz. In total, there were 4 different experiments carried out on the RCDs, and each experiment was repeated 10 times. The first experiment was to see if the RCDs were able to trip in a nominal condition according to the standard. All RCDs were able to trip according to their specification below either 30 or 300 milliamps. The next experiment was to see if the RCDs will also trip for frequencies above the weighted one, above 50 Hz, and it seemed that all RCDs also trip for frequencies above 50 Hz. But they didn't do this according to the standard, the IEC 60479, in which safe leakage currents below 1 kHz are specified. So that's the red line in the figure below, and you see that the RCDs were not able to trip at values below this line, so not according to the standard. And this table shows the maximum frequencies for which the RCD tripped For most RCDs, a higher leakage current was needed to trip the RCDs at higher frequencies. The type B 30 RCD tripped for all frequencies we could test up to 150 kHz, and other RCDs tripped for frequencies between 300 to 500 Hz. The third experiment was to see if a combination of a high frequency tripping current in the presence of a leakage current at 1/2 of the weighted tripping current gives different results. And there were slightly different results found compared to experiment B, but it was unclear if this results due to the increase in fundamental and composite tripping current, and no clear relation was found between the increase in tripping current in both cases. In the last experiment, a high frequency leakage current at a constant frequency and a constant value was injected into the RCDs, and the 50 Hz leakage current was measured. It seemed that the RCDs of type A30 and AC30 have an increased fundamental tripping current in the presence of a high frequency residual current, which can lead to dangerous situations. In the figure below, you see test 1, 2, and 3, where test 1 is the result from experiment A, the nominal condition. Test 2 is an injection of 800 milliamps at 1 kHz, and test 3 is an injection of 1300 milliamps, also at 1 kHz. And it seems that the 50 Hz fundamental tripping current is increasing in both cases above the safe weighted maximum of 30 milliamps. Even up to currents of 300 milliamps are measured, and those RCDs allow these currents for indefinite time to flow. To conclude, the RCDs of type A30 and AC30 show a dangerous increase in fundamental tripping current in the presence of a high frequency leakage current. So this is a false negative situation which results in a serious safety issue. All tested RCDs are sensitive to part of the frequencies above 50 Hz, and this can lead to false positive operation. However, none of the 30 milliamp ones are according to the IEC 60479, for which is safe maximum frequencies currents at frequencies between 50 Hz and 1 kHz are defined. And the standards need to make a clearer definition of the I delta N, because it is unclear if the composite current of both fundamental and high frequency or just fundamental current is meant by this definition. This concludes my presentation. Thank you for your attention, and I hope to receive some questions.